Good afternoon. My name is Jennifer Chang, and I'm working towards the PhD in bioinformatics at Iowa State University. And today we are demoing a piece of software called Mango. It's a C++ software. It runs on Mac, Windows, and Linux. You do not have to compile anything. It is freely available to download. For Windows, we have a setup.exe file that you run. For Mango, we have a DMG, so you just have to drag and drop to applications. And for Linux, you just have to unzip the file. So as I said before, Mango is an environment for combining heterogeneous networks. And part of the reason why I was working on this was because about 2 years ago, I had a gene-to-gene correlation network. And it had 4,000 nodes and about 4 million links. So at first I was working with Cytoscape, and then to load it in, it took about 6 minutes. So a lot of times I had to write command line scripts in order to threshold this network or to get some smaller subnetwork to work with it. And each time I threshold on a different value or based off different criteria, I'd have all this proliferation of all these intermediate network files that I had to keep track of. So Mango was kind of our attempt to make this process a little bit easier. Mango's written in C++. This network, this 4 million link network that took 6 minutes in Cytoscape, takes 30 seconds in Mango to load in. So I'm going to go through what that looks like. It's just standalone software, so you just double-click it and load the environment. And Mango contains a new language. It's a graph exploration language that we developed. You can kind of think of this environment as RStudio for graphs. There's a lot of different languages, so like R is more geared for the statisticians, so your unit of operations is on data frames. Or MATLAB is more geared towards the engineers, so a lot of the operations are geared toward matrices. In this case, we are focusing on graphs. So one of the tasks that you might have is you have a bunch of different networks or biological networks that you want to combine together. Here I've loaded 4 different protein-protein interaction networks. And when you double-click them, they show up in the graph canvas area. And by default, the locations of all the nodes is 0, 0, 0. But I'm going to spread them out. So for each node in Aldo, set x equals 0, y equals some random number between -5 and 5, z equals some random number between -5 and 5. So I'm going to show it on a plane, and I'm going to put these on slightly different planes. And I'm going to color them different colors. And I want to add these 4 graphs together. So I'm going to create a new graph called SOM. Double-click it. And then I'm going to add CPN to it. Add HIF. And notice some of the linkages show up here. And add FRH. And it's a 3D network, so you can rotate it around. I'm going to close the rest of these. And if you do right-click, it runs force-directed layout. So nodes that are connected to each other are pulled close to each other. Nodes that are not connected are pushed apart. For the most part, well, yeah, CPN is not really connected to anything else, so I'm just going to subtract that out. So sum dot minus equals CPN. And then you can just keep working with this network. Now notice in this data area, they have these numbers here. The first number is the number of nodes for that network. The second number is the number of links. I'm going to move this over a little bit. And then if you expand the sum, under the node, you have lots of attributes associated with the nodes or links of a particular network. For the nodes, in this case, like we only have the name, we only have the IDs, and then we have a bunch of attributes with underscore in the front. And those are visual attributes. So generating a lot of 3D network visualization, you're just mapping those informational attributes to one of the visual attributes, and then you can keep exploring the data. So one of the things we might want to do is turn on labels in that case. So we do, for each node in sum, set text equals name. And then that turns on the labels. Or maybe we want to see the connectivity of the nodes. So maybe for each node in sum, set text equals in degree plus out degree. We can map it to radius. So you can change the radius of the nodes. And then in order to turn the text back off, you just set it to the empty string. So let's say we want to set a particular threshold. So anything above connectivity of 30, you want to label it with the name and connectivity. But those hub nodes are kind of like buried in this 3D network. So what I'm going to do is I'm going to map that connectivity to the z-axis. Just a moment. And then it kind of pulls it out so you can see it a little bit better. So this is the most highly connected nodes, HIF1, and it has connections of 137 edges. And maybe I want to adjust that a little bit. You can also turn on the text for the links. It's really hard to see this, so I don't recommend it. I'm going to set that regular again. I'd recommend maybe mapping that to the width of the links. And let's say you have a collaborator who's in another state, okay, and you want to be able to send them your results. One of the things you can do, as long as they have Mango running, all you have to do is send them the 4 tab delimited files for the 4 networks, and then maybe your gel script file. And then all you have to do is do Control-Enter to run each line. If you don't want to send them the whole analysis pipeline, you can also send them just the resulting graph. So I can do save sum.txt, and then what I'm going to do is clear all the data objects in this program. So there's nothing loaded. And then when I run sum.txt again, just a moment, it's loaded back in exactly however you visualized it before. Okay. So I've kind of gone really quickly through the additions. And a lot of my work has been trying to find some standard way of combining networks together. How do you merge information from different networks? How do you merge those types of attributes? So I'm going to run another example with some smaller networks so you can actually see it. So we can use around. Close that one. Zoom in a bit. So we have 2 different networks here in different colors, red and blue. And what happens when we add them together? So I created an empty graph called result. And what I'm going to do is result equals red plus blue. And think about what's going to happen. So when I do red plus blue, we actually have 2 different types of operations, dotted and non-dotted operations. In this case, we only have the nodes from red plus the new links from blue, but not the nodes from blue, not all the nodes from blue. And you can see the new one is this blue one right here, and then they kind of merge the attributes for the color here. I don't know if you can see this, but also between B and D node, like in red, they have a weight value of 0.4, and in blue you have a weight value of 0.3, okay? And because I did red plus blue, it keeps the weight from red. Okay. But if that weight had been 0 or some default value, then it would pull it over. So the order of operations is important. And I can, if you want to learn more about that, I recommend going to the user guide because not much time here. Or come talk to me, of course. Okay, so this is red plus blue. If we did blue plus red, we get that. Red dot plus blue. So this is when you're adding both the nodes and the links together and merging everything. And then blue dot plus red, which results in the same thing. As well as addition, we have subtraction, so blue minus red, red minus blue, blue dot minus red, and red dot minus blue. We have something called multiplication. So what it does is all the nodes in one graph are connected to all the nodes in the other graph. So you can kind of create a bipartite network. We haven't really come up with an operation for division, but if you guys would like to talk to me about something for that, please let me know. And then we have the intersect operator, so the intersection between red and blue. But maybe you want to keep all the nodes in red, and then just intersect the links, or you can do dot and ampersand symbol, or just only the intersection. Okay. So Mango is a standalone program, but you can connect it to online databases. Thus far, we created a dialog window for connecting to the KAG biological pathways. So whatever organism you have, if it's listed on KAG, you can catch it down, as long as you have an internet connection. into this program. So right now there's like 4,072 organisms on KEGG. So for example, Homo sapiens, fetch the pathway list. And then you can choose a particular pathway or just select multiple pathways and merge them together. Wait for it to download. And it tries to maintain the 3D or the 2D layout from KEGG just to make it easier to manage. Now the reason why I'm going through this, I'm going into my next example. So for example, you may have gene expression data, and you want to combine it with biological pathway data. So before this talk, I fetched the 116 biological pathways for E. coli. I'm going to close all these. And each pathway is placed on a different z-axis. I can right-click to let it expand out, or to kind of cluster based off of connectivity. But I've already done that before, so I'm just going to load a pre-existing layout. And then we only really care about the green and blue nodes. So the green nodes are enzymes, and the blue nodes are compounds. Therefore, the gene expression data is going to map to the green nodes. Let me just lay this out. And I'm going to load in the microarray data. Yeah, there's no linkage information in the expression data. But if you expand the expression, for each node you have a control value, a treatment 1 and a treatment 2. So I'm going to add them together with the pathway data into this sum network. And some of them don't map, so they have the default XY values. So now I might want to color them. So I've colored the genes gray for now, and then I've kind of reduced the radius of the compounds because we don't care about the compounds yet. And then for each node in sum, where treatment 1 is greater than control, set it to this green color. For each node in sum, where treatment 1 is less than control, set it to this red color. And we kind of want to look at pathways. So we can also highlight the links. So if 2 green nodes are connected, you color the link green and red accordingly. And that way you can highlight the entire pathway and zoom in and zoom out and continue to explore the data. You can turn on the text for just the green. Kind of hard to see. Turn those off. You can collect subgraphs. So you can create a subgraph red and a subgraph green. And you can export those 2 files as tab-delimited files to analyze it further in R or Cytoscape or whatever you want to use. Or you can just save the graph and then reload into Mango. So if you wanted to continue analyzing this data in Mango, maybe let's focus on just the green graph. So what I'm going to do is lay it out as a circle. It's just randomly placed along the circle. And then I'm going to map connectivity to height. And I'm going to give them random colors for now. Reduce the width of the links. And then I'm kind of bleeding the colors down into the links so it can emphasize the hubs a bit better. Move this around. And then I turn on the connectivity. And maybe I only want to see the highly connected ones, but I need to choose some type of threshold value in order to determine which ones are my hubs. So I can look at this and think, well, maybe I want to choose a threshold value of 12, for example. Anything above a connectivity of 12. Now let's increase those hubs, increase the radius of those hubs, and just turn on the text for that. There we go. And then I want to mainly focus on anything that's connected to a hub. So I can create a new graph called hubs. And it only keeps anything that's connected to a hub. So let me right-click and let it lay out. And kind of cluster together. And maybe I want to flatten this graph. If I want a 2D image of this graph, I guess. And the hubs are still kind of buried in there, so anything that's a hub I'm going to raise to a z-value of 4. So you have one layer. And then maybe you're interested in genes that are not hubs themselves, but connect to hubs. So I've been calling these in-betweeners. And then I'm going to put them on a z-plane of 8. So they're up here. And then I can pull out these in-betweeners and hubs into a new graph called betweeners. And I can lay out the hubs along the left and lay out the in-betweeners on the right and turn on their names. And then I can start to look up each one of these connections and try to figure out some more information from the data. Thus far, we've shown a lot of visualization and analysis examples. We've just gotten while loops to work, propagation of values to work, so you can actually do computations on this. And those are you who are familiar with cellular automata. This is a nice tool. So I'm going to create a cellular automata example that's laid out on a torus. The key thing about cellular automata is the state of being alive, or a particular node being alive or dead is dependent on its neighbors. So if there's 3 alive around it, then it'll be alive. If it's over 4, then it'll die, or if there's no one else around, then it will die. So I'm going to give them random states. Red is alive, green is dead. And then I'm going to let it run. And you can rotate it as it keeps going. So there's lots of examples of how you might use this tool. Feel free to come talk to me. I would be happy to discuss it. If you haven't gotten a card yet, please come talk with me, or I have a box right up here. It's freely available to download. It's free to use. You don't have to compile anything. We've worked hard on the installation files. And let us know. Thank you.
Where does it run?
Mac, Windows, Linux. Windows 7 and 8, 7, 8, and 10. Mac after 10.9. Linux.
So basically, all the modern computers can run Mango, and it's written in C++, and it can handle. We didn't have the time to demonstrate, so it can handle graph millions of links. So this is really for big data.
Although it can work with small data too, but
right.
It's scalable.
Of course, if you can work with big data, you can work with small data. Right.
Any other questions? How about 32-bit support? I noticed you're running a 64-bit, so it doesn't matter whether you're on 32 or 64. Does it affect the performance overall?
It may affect performance. Well, it shouldn't.
We have 32-bit version and
Yeah.
64-bit version. Just pick the one that fit your platform. You could run 32-bit on 64-bit platform, but it's not advisable.
So we have 32-bit version this one.
Yeah, that's all the available platform right now we support it.
Okay, there's thanks.